This is the beginning of Lecture 9, where we will be covering some examples of our remote sensing platforms in a general context. We try to describe some of the general platforms, and then the other half of this lecture, we're going to look at some specific satellites. Satellites that have been sent out by various countries, and we will go through these the different satellites with a general idea of the area they swap with, the intent of these satellites, the accuracy of these satellites. There's an extensive list of satellites, and my intent in this lecture is just to give you a taste of some of the common satellites being used. One of the first type of satellites used historically is one which is ground attached. It's used for special purposes involving small, low-level vertical photograph or vertical remote sensing surveys, and it's particularly done in reference to archaeological applications, as they dig around area of interest and start an archaeologist finds any important artifacts, and they want to map exactly where they found that particular artifacts within the area of their exploration. They would use a ground attached satellite or a ground attached vehicle. It is low level. It will give a very detailed description in terms of capturing what is being done progressively, and it could capture visible portion of the spectrum and other part of the spectrum, infrared, whatever we want in terms of the sensors that we have on that low-level aircraft. It's most convenient to use because it's attached to the ground, and you can vary the flying height, you can move it around and get much more information. These ground attached includes towers, mobile cranes. Mobile cranes are where you can have a bucket attached to the crane, and then the bucket has a sensor or a device that captures or the reflectance value. Or it could be hydraulic platforms or even kites. Now, kites can wander around, but um, for a day where we have a calm wind environment, meaning the, the 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 wind, it's not a windy condition. It's an ideal and cheap way of getting a platform up and running, but it's not commonly used, however. And balloons, of course, balloons where we can attach our sensors to the base of the basket of the balloons. So there are many other types, many types available which are ground attached. They're very inexpensive to buy or you can hire, or if you want to rent them, you can get them readily available. It has the advantage of exact positioning. Because it's ground attached, we can move it around to exactly where we want the sensor to be. All such platforms can be manned. Usually they can be manned, meaning that we can have someone on board where the sensor is. Useful for making low-level oblique images, and we can have also stereo images where we have two photographs of the same area being captured. Using those stereo pair images, we can create 3D models. Very. The other type of platform is small airborne platform. It includes drones, helicopters, and free flying balloons. Drones, they are unmanned, and it's controlled by a remote control on the ground. used to fly over enemy lines during the time of war. It's a very small version model aircraft. On the aircraft itself, there is um, the sensors at the base of the aircraft that can take out visible portion of the spectrum, infrared portion of the spectrum, etc. Helicopters, they're more expensive than the typical survey aircraft, but the advantage of the helicopters is that they can hover around the area of interest and also can vary the height, the flying height of the helicopters. Free flying balloons, we can get oblique imagery. Because it's free flying, we don't have much control, but it's only one way of getting imagery. Another type of platform is your survey aircraft, and these are more commonly used for photogrammetry. Even though it's used for photogrammetry, we can use it to capture other parts of the spectrum in terms of changing the film type in the cameras, or we can even have the various sensors at the base of the aircraft capturing electronically the reflectance value from the Earth's surface. What you see here is a table of comparison of the different aircraft type, the cruising speed, the flying height, and the number of sensors they can have. They typically would have. For example, a single engine, its cruising speed is 140 knots. Maximum flying height is 14,000 feet, and usually it's adapted with it's equipped with one sensor, as compared to a commuter aircraft type, where we can have 8 to 12 people on board. Cruising speed is 190 knots, and the flying height is 25,000 feet, and we can have two sensors. A spy plane, cruising speed is more than 1,500 knots. Flying height is 120,000 feet, and we can have two or more sensors. So depending upon what type of data, what data you're looking for, we can choose the different type of survey aircraft. And the price is closely related to the type of aircraft you're looking at and the type of imagery that you're looking at getting. The different types of survey aircraft suit different types of remote sensing mission. So based upon what their client specification, we will choose the appropriate survey aircraft. Smaller ones are hired for short periods within the operational limits and also within the budget as defined by the client. Larger aircraft are typically not used to cover small areas. You want to get a small aircraft to fly to capture more detail. However, for flying blocks of photograph, they're ideal. So it all depends upon the project, the specifications as defined. The other type of platform is the Earth orbiting platforms, and this is where we start getting out of the small area of mapping, but looking more at a large, expansive area, a global context. If we want to look at movement of ocean currents, or even looking at wind direction, wind speed at a global context, we will be looking at getting some Earth orbiting platforms that are orbiting the Earth's surface. And because we are talking about having these huge equipment orbiting the Earth's surface, they can be very, very, very costly. Imagery obtained from its orbit as it's sweeping the Earth's surface, it's continuously capturing images directly beneath the satellite, and also some of those satellites have sensors that collect oblique images also. It typically covers large areas because of the high altitude, and these are the platforms that has ground receiving stations. So the data is usually transmitted to ground receiving stations located at different locations on the Earth's surface. Lower resolution than the aircraft product because of the high altitude they're flying at, and also looking at the high altitude, the thicker atmosphere, the cloud cover need to be taken into consideration. There are various platforms considered based upon the altitude of the orbit, the inclination of the Earth's axis, time spent in orbit, the number of sensors, whether it's manned or unmanned. So there are various types of Earth orbiting platforms. For example, there is the American Space Shuttle. The Challenger accident delayed the shuttle program. A lot of you may would have heard or read about that. The platform, the shuttle, had several advantages over satellites. Each mission, the orbit can be different. You can vary the orbit. There was a crew to operate the sensors on board. There was enough power to operate several sensors, and a lot of these satellites actually harness the solar energy from the sun, so they would have solar panels to convert or use the sun's energy into electrical energy. Shuttle mission, during the shuttle mission, they also had a metric camera that took about 1,000 photographs, which was used to create stereo model and do a lot of other things. There are other manned satellites that historically has presented itself, and you may have read about it in journals and in books. American satellites are Mercury, Gemini, Apollo, Skylab. Skylab was the one that actually fell out of orbit. However, Skylab is the only one that provides images of real scientific importance. Unfortunately, it fell out of orbit. In the mid-1970s, Skylab orbited at 435 kilometers and passed over each point on the Earth's surface between 50 degrees north and 50 degrees south latitude. It contained a multispectral scanner, which we spoke about in previous lectures. It also contained a microwave radiometer. So it was actually making use of the microwave portion of the spectrum. It took over 35,000 photographs of high quality. So yes, it was unfortunate it fell out of orbit, but it did a lot of good. There's also the unmanned Earth resources satellite. This is more commonly used, and what is done is that quite a few countries would send up their unmanned Earth resource satellite to look at different aspects of the Earth. If you're looking at mapping vegetation, or if you're looking at mapping global pollution, there are different types of satellite that will facilitate the data, will provide the data or sends the data so that scientists can make use of that data to do their analysis. Now, the unmanned satellites, they operate, these are satellites that operate in a near polar sun synchronous orbits. So when you see near polar, it's in temperate region, and they're also sun synchronous, meaning that they are highly dependent upon the sun's energy. So they will be following, or the orbit will be in sync with the rotation of the Earth, such that the satellites would always be getting energy from the sun. Other orbits are possible. There's one that near equatorial orbit of the tropical Earth resource satellite. That's a possibility. There are quite a few satellites that has various orbits. All orbits are in the range of 600 to 900 kilometers and are so designed that the satellite can cover its different portions or different areas on the Earth's surface that is of interest. Two popular unmanned satellites, when you talk or read any journal about remote sensing, is your Landsat satellite, which is American-based satellite, and Spot satellite, which is a French-based satellite. Satellites have passive sensors only powered by solar panels, so the energy that is reflected from the Earth's surface is the only energy that is being recorded by the various sensors on the satellites, on the unmanned satellites, in particular Landsat and Spot. And they're totally dependent upon the sun's energy via its solar panels, which will capture that energy and convert it to electrical energy. Camera photography is not used because of the problem of retrieving film, but that has been improved upon in that if any visible portion of the spectrum is captured, it's sent electronically via electronic means and to the ground receiving station. So long ago this was a big concern, retrieving the film, but now it's not a problem, so it's available. There's also another general category of satellites, which is the unmanned meteorological satellites. They have a different orbiting requirements. We want to use satellites. We have been using satellites to look at weather changes and weather patterns. They are required on a daily basis. More frequent coverage is required, but not necessarily of high resolution. Usually, the use of it is for medium altitude. When I say medium altitude, if height is around 500 to 15,000 kilometers, and some of them are near polar orbits, or it can be very high altitude, at least 35,000 kilometers, and it can be geostationary orbit. So the meteorological satellites is another big category. Weather stations, weather TV stations do have their own satellites that they would use, to get reliable information regarding weather conditions. A typical near polar sun synchronous satellite does between 14 to 15 orbits per day. So on average, a satellite would do 14 to 15 orbits, passing each point on the Earth's surface at the same time. There is also a common method, or a common SWOT width of a sensor called Advanced Very High Resolution Radiometer, and the altitude there is 3,000 kilometers at an altitude. The SWOT of that is 3,000 kilometers at an altitude of 830 kilometers. So this is a common radiometer being used by quite a few of the satellites. The geostationary satellite orbits are above the equator and have an orbit of one period for 1 day. Sensors recorded every 30 minutes during the daytime, so a lot of information captured in over a day's period for geostationary satellite, and it's very useful if you want to look at changes over a period of, if you're looking at forest fires, a geostationary satellite is going to be very useful. Another category of satellites is your military and your experimental Earth observation satellite. Because it's military satellites, not much is known about these satellites. Their orbits can be varied. Sometimes using thrusters, they can vary the orbit. Can be very low, very low to get a close look. It can lower the orbit so that you can get more detailed information. It can increase the orbit for whatever reason, there are much more flexibility, and this is controlled by the ground receiving station. So it's unmanned, but it's also being controlled by your ground receiving station. Some can move around to change their orbits. Some carry electro-optical scanners, while others carry frame cameras long ago, but this is a bit outdated. If they're taking out any photographs, it will be sent telemetry to the ground receiving station. Main characteristics is the ability to acquire very high resolution images of small areas. So yes, there's very little known about military satellites, but it's speculated that the information from these satellites are very good in terms of the resolution of the images. This is an example of North America infrared image. I got this from online, NOAA.gov, where you see a vector data set of North America, the boundaries, overlaid with imagery of the cloud cover showing the directions of clouds, the wind directions. So there are many different types of imageries, but I just want to show you, this is readily available online to view, to query. If you need to get the data at the various ground receiving station, you would go to their website and fill out the necessary forms. Some of them might be free, some of them you might have to pay a nominal fee, but the data is available. Now, this list you see here is a sample list of satellites which I got online, and it's an extensive list. I just wanted to show you the different names of satellites that occurred ever since it started sending up satellites to orbit the Earth's surface. And the names, some of them might not be existent yet again, but just to give you an idea about the number of satellites, I only downloaded the list from A to E. The list goes on and on. You can check this website. But just to give you an idea of the multitude of satellites. Let us look at some of the other satellites, a sample of them. And to keep it simple, I will classify them as follows. I've classified the sensors, the satellites, in following categories. We have moderate resolution land satellite, high resolution land satellite, hyperspectral satellite system, meteorological satellites, ocean monitoring satellite, Earth observing system satellites, space station remote station satellites. These are some examples of some moderate resolution land satellites. I cannot give you the extensive list of them because it's a long list. However, let's look at some of these, some examples of these. When we go through it, I just want you to note the type of resolution, the type of sensors they have on these different satellites, general characteristics of them. You have the IRS system, which is Indian Remote Sensing Program. They launched their first satellite, which is IRS-1A, was launched in 1988, and they had another version, IRS-1B, in 1991. Those satellites were sent up from India. The satellites were equipped with a multispectral scanner. There's a second generation of the IRS satellite was sent up in 95 and then in 97 respectively. They carried 3 sensors. It's a summary of the IRS satellites, and if you notice here 1A, it captured the blue-green bands, and the SWAT width was 148 kilometers. Resolution, pixel resolution was 72.5 meter in the blue band, and then 36.25 in the green band. And the coverage date, repeat coverage days, it took the satellite 22 days. But as you go down the list in the different generations of the IRS satellite, you can see the number band has increased, and the spatial resolution has improved actually. And then the repeat coverage has increased from 22 to 24. SWAT width, it has reduced a bit by a few kilometers. IRS 91D, it was launched in 97. It also carried a panchromatic sensor. So there has been and the panchromatic sensor provided oblique images. Resurs 01 is a Russian satellite. Was launched. The first series was launched in 1985, operated for 3 years, and the second satellite was launched in 1988, and that served for 7 years. The third satellite began in 1994. The Resurs satellite carried multispectral scanner, spatial resolution of 170 meters, in the 4 visible and near infrared bands. Revisit days is 4 days, which is a big difference. The size of the scene is 600 by 600 kilometers. A Japanese satellite called Advanced Earth Observing Satellite. It was launched in 96. It carried 2 primary sensing systems. Your advanced visible near infrared radiometer, so it was actually looking at the microwave portion of the spectrum, and ocean color and temperature sensor. And for Japan, this was very useful for them since they have a lot of bad weather, typhoons, etc. The radiometer data collected in 4 bands using a multispectral mode, and the temperature sensor recorded in 8 bands in the visible and near infrared, and 4 bands in the thermal region. So the Japanese satellite certainly did need all of this type of data in order for them to better predict or address some of their weather concerns. Another satellite, it was the GIRES-1, primarily a radar remote sensing mission. Is Japanese, launched in 92, carried out using the optical sensor, spatial resolution of 18 by 24 meters, employs a push broom scanning. It scanned 7 bands in the visible and near infrared and mid infrared. Another big category of land satellite is your high resolution land satellite. Numerous examples of these are launched or in continuous development stages. These are some examples which we'll go and look at in briefly to look at in terms of the characteristics of them. SPIN 2, it's Russian, first mission in 1998. Space information, it's called Space Information -2, hence the acronym SPIN 2. Data is produced by digitizing your panchromatic photograph taken by a particular camera. This is the type of camera that they have equipped with SPIN 2. The altitude of the satellite is 220 kilometers, and the individual scenes is 40 by 160 kilometers. Econos, this is a common satellite. It's launched in 1999. Repeat days every 11 days. The coverage seen is 11 by 11 kilometers. Collects in 4 bands at a ground resolution of 4 meters, so that's pretty good. System is highly maneuverable, which means that it can zoom in and zoom out. It could also even change altitude, which is a QuickBird is another satellite commonly referred to in books and in journal articles. It's done by Earthwatch Incorporated, launched in 2001. High resolution data obtained at an altitude of 600 kilometers. Repeat or revisit day is 1 to 5 days, and the resolution, panchromatic mode, is 1 meter, and 4-band sensor with a resolution of 4 meter. So in panchromatic or black and white mode, the sensor there, the accuracy is 1 meter, and the 4-band sensors is 4 meter. OrbView 3, developed by a company called GeoEye at the time, launched in mid-2000. Altitude is 420 kilometers. Revisit days is 1.5 days, with OrbView 3 and OrbView 4 operating simultaneously. So if I use OrbView 3 and 4, capturing the same image at the same time, we can use those imagery to create stereo models or 3D models. It includes a panchromatic band, which is 1 meter resolution, and 4 multispectral bands, which is 3 meter resolution. ERAS, developed by ImageSat International. This is another satellite that is commonly referred or used in many research, and you would have read about it in journals and in books. Joint between Israel Aircraft Industries and Core Software Technologies. The Type 2 ERAS A Plus launched in 2000, and there's another one in 2001. It utilizes push broom scanning, panchromatic system. The resolution here is 1.8 meter, and the SWAT width is 16 kilometers. Another big category of satellites is your meteorological satellite. It assists in weather prediction and monitoring what changes in weather conditions. Uses sensors that have coarse spatial resolution, meaning it's not going to be high quality, because we'll be looking at larger area, not very detailed in terms of the pixel resolution. It's not a requirement. Various countries have launched various meteorological satellites. Some of the well-known meteorological satellites that are US based are your NOAA satellite, National Oceanic and Atmospheric Administration satellite. You have the Geostationary Operational Environmental Satellite, GOES, and then you also have the Defense Meteorological Satellite Program. All of them carry a range of specialized sensors. There's also another group of satellite, which is your ocean monitoring satellite. These are specifically designed to map or sense or cover the Earth's surface, the aquatic portion of the Earth's surface. Why? Because 2/3 of the Earth is covered by water, and these satellites provide synoptic views of the ocean over large areas and over a large extended period of time. It's particularly useful for monitoring pollution, especially in areas where they're drilling for oil, offshore drilling. Examples of these ocean monitoring satellites are CSAT. It operates in the microwave portion of the spectrum, so it's not dependent upon the sun's energy. Another example of your ocean monitoring satellite is your Nimbus 7, also called Coastal Zone Color Scanner. It measures the color and temperature of coastal zones. And there are many other types of satellite that's associated with monitoring the aquatic portion of the Earth's surface. Now, these satellites carry other specific sensors as it relates to monitoring the ocean areas of the Earth. Now, all of these satellites that I mentioned to you, as I said before, it is only a small subset of the magnitude of the multitude of satellites orbiting the Earth's surface. They all have ground receiving stations, which I mentioned in previous slides. These ground receiving stations are designed to collect the transmitted data from the satellite, where it's post-processed. The end users would get the data from the satellite, not directly from the satellite, but from the ground receiving station, because the ground receiving station will have to post process it, that is, remove errors, define coordinate system, filter the image, remove the effect of any errors associated with taking an image at such a high altitude. It also would remove the effect of cloud cover, a lot of other good things about post-processing the raw satellite data. This is an example of ground receiving stations for Landsat satellite. There are quite a few, of course, in America and all over the world. South America, Europe, Africa, Asia, and all of these satellites would have a ground receiving station map. Alright, this concludes our talk about remote sensing platforms. Go over the notes, make sure you understand what's going on. Download the PowerPoint presentation notes page and review it, and we will continue with our next lecture.